Good morning, ma'am. I'm Tejaswini from CSO. So, my topic for today's seminar is diffraction. So, firstly, what is diffraction? The phenomenon of bending of light waves incident on the edge of the opaque obstacle and spread with geometrical shadow is called diffraction. That is, let us consider an obstacle like this, that is AB, and let's consider a screen XY. So, when the light from source S, which is placed here, uh, hits this obstacle, hitting the edge of this obstacle that is at the point B, it bends, that is, its direction changes, and instead of going in the normal direction as per its properties, it bends and reaches another point to give a different image like this. That is this image ID, unlike the normal image we get IO, that is the original image, while this ID is nothing but the diffraction image. And we can observe this diffraction phenomenon in all the waves of sound waves, water waves, heat waves, and light waves too. So now coming to the types of sources, that is the types of light sources like we have taken in this example. The light source in this example is the point source type, and the other types of light sources are linear source, that is those sources which are represent like a line or line segment. And the third type is infinite distance source, that is the light source which is kept at a very infinite distance. Now, as we talk about light, then we come to the topic of waves. So, and then wavefronts. So, what is this concept of wavefronts? The scientist Huygens proposed the concept of wavefront. The locus of all same phase particles is called wavefront. That is, as we can see in this example one more time, from the source, a light ray is passing in this direction. Even though we only mentioned one light ray in this diagram, there will be, of course, a lot number of light rays coming from this light source. That is like this and like this, and these all light rays represent something called a group of light rays, which is nothing but a wavefront. And again, these wavefronts are further divided into three types. That is, first one is spherical wavefronts, second one is cylindrical wavefronts, which are in the shape of cylinder, and the third one is plane or linear wavefronts. So, and if we talk about the shape, these wavefronts are divided into three types, which we just discussed. But based on the location between the two screens, these wavefronts can be classified into two types, that is the primary wavefront and the secondary wavefronts. Now let's once again see the previous example we had taken, that is we have taken an obstacle AB and light from the source S is passing and hitting this obstacle AB. Now before hitting the object, the light from this light source, that is all the light rays, this represent a wavefront which is nothing but the primary wavefront. While after hitting this obstacle and passing once again, the light gets reflected and also gets refracted, and this due to the diffraction, the light gets goes into different angles, that is different angles of diffraction, and forms again once again a set of light rays which gives a different wavefront. And now this wavefront is nothing but called as secondary wavefront. That is, after, before hitting the obstacle, it is called as primary wavefront, and after hitting the obstacle, it is called as secondary wavefront. Now that we know what is the meaning of wavefront, let's move on to other topic. That is the differences between interference and diffraction. So interference is a topic which we are familiar with since it is the first unit of our syllabus. So firstly, we know that interference is observed in all the waves, which is the similar property for diffraction too, because as we discussed before, diffraction is also observed in all the waves. Interference is proposed by Thomas Young, while the diffraction is proposed by Grimoald. That is, a scientist called Francesco Grimoald has proposed this phenomenon diffraction. And also, interference is a modification of amplitude intensity with superposition of waves, which we discussed before. It is the result of intersection, or should we say collision of two different ways of different characteristics to form a resultant wave, that is a constructive interference or destructive interference, which were discussed previously, while the diffraction, which we discussed just now, is the phenomenon of bending of waves and spread with a geometrical shadow. Interference is observed in daily life in soap bubbles and oil drops in water, while the diffraction is also observed in daily life. It is observed in CDs, DVDs, shadow microscopes, telescopes, and photographs. And intensity, amplitude are equally distributed for this interference, while in the case of diffraction, intensity and amplitude are not equally distributed. We can clearly see this point in these graphs here. For interference, the representation of these waves are clearly equal, that is with equal amplitude. Either that is for amplitude or intensity, these are equal. But while in the case of diffraction, we can clearly see that there is a irregularity in the amplitudes or intensities according to the graph for their magnitudes. And interference pattern are bright images and dark images, while the diffraction patterns are maxima and minima. That is, we can clearly see in this, because unlike in interference, in diffraction we have different amplitudes, magnitudes of amplitudes or intensities, so there will be of course maxima and minima. So this diffraction pattern refers to maxima and minima, while interference pattern refers to bright image and dark images, which are formed later on the screen. Now coming to the next topic, Fraunhofer single slit experiment. This is one of the main experiments in this chapter. So let's see the construction of this experiment. In this experiment, we'll take two convex lenses, that is L1 and L2, and we'll take a slit, that is AB. In this experiment, we'll only consider a single slit because, as its name suggests, it is a single slit experiment, and a screen, say XY. And what happens here is, from the source, that is the light source, which is kept at an infinite distance, the light rays hits on this lens L1, and after passing through the lens, they become parallel to each other in a straight line waveform. And after passing through this slit AB, what happens is, firstly, we can say that they follow the normal path according to this to the properties and forms the original image I naught. But due to this edges of the slits, that is at A and B, what happens is the light hits these edges and undergoes the property of diffraction, that is it gets bended and forms another image ID, which is our diffraction image. And also we have to note that before passing through this slits, it is considered, this whole part is considered as light rays, which represent the primary wavefront, and this second part after passing through the slits represents the secondary wavefront. And this is the whole concept of Fraunhofer single slit experiment, which shows how the light rays from the infinite source, after passing through the convex lens and passing through the screen, takes different paths to form two images, that is an original image, and after going through diffraction, a diffracted image. Now, as we mentioned before, here ID is diffracted image, I naught is the original image, and as we can clearly see that in diffraction takes place with different angles of diffraction. So let's consider the angle theta here. Here this angle theta represents the angle of diffraction, and this BC represents the path difference S. Here path difference is nothing but how much the diffracted light rays are in difference in terms of path with the normal path of the light rays, which forms the original image. And we'll consider this whole length of the width of the slit as A units. Now we've seen all these terms. So let's see the derivation of the path difference in this experiment. Now let's consider the sine of the angle of diffraction, that is the sine theta here. So clearly we know the sine of an angle is the opposite side by hypotenuse, that is BC by hypotenuse. This is the right angle. Hypotenuse will be AB, that is equals to A units. So the sine theta will be BC by AB, that is equals to S by A. From this we obtain that path difference equals to A sine theta. This equation represents the path difference of the diffracted light in the experiment, that is our current single slit experiment. Now let's see in different how it changes in different cases. As we studied in the lesson of interference, there will be maxima and minima. So for a path difference to be maximum, it is equal to n lambda. So here path difference is nothing but a sine theta, which we derived here. So a sine theta equals to n lambda, where in case 2 a sine theta equals to 2n plus 1 lambda by 2. That is in case 1 it is the condition for maxima, while the case 2 is the condition for minima. Now as we discussed before, x is the distance between the original image and the diffracted image, that is this distance. That is the distance between IO, original image, and ID, diffracted image. So now let's determine the distance x between this original image and diffracted image. Before we derive that a sine theta equals 10 lambda for the maxima condition. So in this condition, theta will be very small. As theta will be very small, we can also say that sine theta can be approximated to the value theta itself. So substituting this sine theta as theta in this equation, we get that a theta equals to n lambda, and from then we get that lambda equals to a theta by n. Now this equation represents the diffraction angle, size, and gives us the value of wavelength. And from this, since we obtained an equation for wavelength, we know that distance between the original image and the diffracted image depends on the focal length of the lens, wavelength of the light, and the size of the slit. We know the size of the slit from the experiment, which is a practical value, that is A, and f is the focal length of the lens, which is also a practical value which we can obtain from the experiment, while lambda will calculate this lambda value from this equation we obtain. Thus we can say that the distance between the original image and the diffracted image, x equals to f lambda by a. Now let's see distribution graphs for this experiment in clearly. We've seen this graph before. So for the single slit experiment, this will be the graph of amplitude or intensity with phase. There is its maxima is at the middle, which is nothing but principal maxima, and all the uh, other slopes are other consecutive maxima. That is for n equal to 0, it is principal maxima. For n is equals 1, that is first order maxima, and it so goes so on. Thus, as we know that amplitude and intensity are proportional, so the graphs will also be similar, with the main maxima, principal maxima in the middle, and while the other maxima at the sideways as per the value of n. Now the number of orders in this single slit experiment, that is for different values of n. That is, if n equal to 0, it is called 0 order spectrum. That is, this spectrum is nothing but this graph. So only that graph, if n equal to 0, only contains this middle slope, middle principal maxima. For n equal to 1, it contains this middle slope, and it is this part. So as per the different orders of this experiment, that is values of n, the graph extends respectively. So for n equal to n, it is called as nth order spectrum likewise. Now the next topic is double slit experiment. That is, in this experiment, the setup is the same like in the first experiment, but instead of one slit, that is single slit, will take two slits. So similar, the arrangement is similar as in the first experiment, but here we are taking two slits of width A, that is this slit and this slit, and the distance between these two slits is A plus T. And remaining all other elements are same, that is x is the distance between original image and diffracted image. But here let's see how the light path takes place. The light comes from the source S, struck the convex lens, and it passes parallel beams of light, hits these two slits, and after hitting the edges of the slits, it undergoes diffraction and normal, and also its normal path. So the diffracted light forms this image, diffracted image ID, and the normal path of the light creates the image, that is the original image. Now, like in the previous experiment, let's find the value of sine theta, the angle of sine of angle of diffraction. Once again, here this is the angle of diffraction. So in this triangle PQR, sine angle of the theta is opposite side, that is QR, by hypotenuse, that is PQ, where QR is nothing but the path difference S, while PQ is the distance between the slits, that is A plus D. And substituting these values of uh, QR and PQ, we can get that sine theta equals to S by A plus T, and on for sending the value of A plus T to the other side, we get that path difference S equals to A plus T sine theta. Now this equation represents the path difference of this double slit experiment. Now similarly, if we take the conditions of minima and maxima, for maxima path difference equals 10 lambda, so A plus T sine theta equals 10 lambda. For minima, it will be A plus T sine theta equals to 2n plus 1 into lambda by 2. Now if we see the amplitude intensity graphs, it will be similar to the first experiment, that is the single slit experiment, but the only difference here is that we can only get either one of these two cases, that is either we get the even order as missing part or the odd order at the missing part. Either, that is only we can get either one wavefront, that is the wavefronts with orders n equals to 2, 4, 6, 8 at the same time, or the wavefronts that equals to 1, 3, 5, 6 at the same time. So we'll only obtain part of the graphs for this experiment each time, like this. Now coming to the next experiment, that is Fraunhofer and slit diffraction. Unlike in the previous two experiments which we have taken one slit and two slits, in this experiment we'll take n number of slits. That is the only difference in the setup of this experiment. So let's see how the light travels here. There is light comes from a source S, struck the lens L1, goes into the parallel beam of light. So this up to this part it is primary wavefront, and after hitting the slits it gets it gets into two parts, that is a diffracted light and the normal light, which continues as a parallel beam of light, and on again further hitting the lens L2 it get converged at this lens as I0, which is the original image, and this diffracted light after hitting these edges is ID, that is a diffracted image similar in the previous cases. So even though n slits are present, the distance between the first and the last slit does not change, which is equals to AD, similar to the previous case. So let's see the derivation for path difference, that is QR, that is S equals to QR equals to S in this experiment. A sine angle of theta, that is the angle of diffraction, is clearly we can see that opposite side, that is QR by hypotenuse, that is BQ. So QR is S and hypotenuse BQ is nothing but the distance between the first slit and the last slit, that is A plus T. So sine theta will be BR by PQ, that is equals to PR by A plus T, where PR is nothing but path difference sigma. Thus we get path difference sigma equals to A plus T sine theta in this experiment too. And we have to note that this equation represents path difference for multiple number of slits. So now conditions for maxima and minima. We know that for maxima it is equals to n lambda, path difference equals to n lambda, so sine theta into A plus T equals n lambda. And in the case 2 for minima, path difference A plus T sine theta equals to 2n plus 1 into lambda by 2. Now in this case 2, the intensity and amplitude graphs will be same with different maxima and minimas for different orders. That is, the center there will be principal maxima, and all the remaining are different maximas at their own orders. That is, for n equals to 0, we obtain only principal maxima. For n equals to 1, we obtain extra of first order maxima on both sides of the y-axis. For n equals to 2, second order maxima, and the list goes on as per how we take the order in the experiment. Now these are the main three experiments and their respective graphs and results of path differences. Now let's see the next topic, which is grating. The main points of this concept are: diffraction grating was first invented by Fraunhofer, who is the main scientist in this chapter, and grating works with two types, that is, there are transmission grating and refraction grating. Grating consists of many number of spectral parallel slits. That is, it contains uh, a huge number of spectral parallel slits, which, like how we have seen how different number of slits in the previous experiment, this contains many number of spectral parallel slits. The path difference of the light in Fraunhofer diffraction grating is represented by A plus T sin theta equals to n lambda, where A plus T combined width of the multiple slits, that is 1 by n, where here A plus T is not equals to 1 by n, where n is nothing but the number of spectral lines. That is how many lines are passing through this consecutive slits. Now, so since it's given in this equation, n lambda equals to a plus t sine theta, on replacing the value of a plus t with 1 by n, we get that sine theta by capital N equals to small n into lambda, where small n represents the order, lambda represents the wavelength of the light, capital N represents the number of spectral lines, and theta represents the angle of diffraction, like how we seen in previous experiment. Now, what are the applications of this concept of grating? Firstly, it is determination of light wavelength. Grating equation is represented by a plus t sin theta equals to n lambda, which we have seen before. That is a plus t then equals to 1 by n. So we'll substitute this value in this equation like before. We get that sin theta by capital N equals to small n lambda, and from there we can get the value of lambda, that is wavelength of the light, which is equal to sin theta by small n into capital N. In the similar way, by rewriting this equation, that is small n lambda by small n lambda equals to sine theta by n, we can obtain all the values, all the unknowns in this equation, that is either the wavelength lambda, which is equal to sine theta by small n into capital N, or theta, which is angle of diffraction, equals to sine inverse of n, that is small n into capital N into lambda. Or we can also obtain the value of small n itself, which is the order in this experiment, which is equals to sine theta by capital N into lambda. And we have to note that, as we discussed before, capital N is nothing but the number of spectral lines, which is equals to 15,000 lines per inch. That is 5,905.5 per centimeters. That is, in this concept of grating, we consider the value of n as 15,000 lines per inch, or 5,905.5 spectral lines per centimeters. Now the next concept is resolution. So what is resolution? The phenomenon of separating two closed overlapping colors. So there is sometimes we can see in the range of visible light, some colors are appears to be overlapping. So by the process of separating these two colors with a slight difference in their uh, respective wavelengths is nothing but called as resolution. And next, what is resolution? Resolving power. The capacity of optical instrument to separate these overlapping images. That is, as we discussed now just now, resolution is nothing but the separating of these two overlapping colors, while the equipment required for this, that is the capacity of this optical instrument to separate the two overlapping images, is nothing but resolving power. And we also know how to note the point that human eyes has resolving power too. This is seen before. We can clearly see the difference between colors, even with the slightest difference in their wavelengths, right? So, which is nothing but because thanks to the resolving power of our human eyes to differentiate between different colors. Otherwise, we'll be suffering from a disease called color blindness, but which is not the case, but thanks to the resolving power of our eyes. And the next is the concept of Rayleigh criteria of resolving power. So the scientist named Rayleigh proposed the criteria for resolving power in three different stages. That is before resolution, that is before the process of separation of these two colors which are similar. and during the resolution and after the resolution. These are the three main steps in this Wiley criteria. So before resolution. Now let's consider two similar colors which are overlapping with each other. Say lambda 1 be the wavelength of the first color and lambda 2 be the wavelength of the second color, that is second spectrum color. As we can clearly see that before resolution these two colors of different wavelengths lambda 1 and lambda 2 are clearly overlapping with each other in this part, and the resulting completely new uh, completely new color similar to both of them, a resulting graph because they are overlapping. But during resolution, what we'll do is we'll separate these two colors with different wavelengths, separating from each other. So this common part will be disappeared, giving a dip. There is the R minimum, unlike in the previous case, which is the maximum, as the result is from their overlapping. Since we are separating them from their overlapping, this graph gives a result of R minimum, which is nothing but we call as dip in this experiment. Now after resolution, these two overlapping colors with different wavelengths, which are bit different in the magnitudes, that is lambda 1, lambda 2, are separated, and we'll get graphs of separate wavelengths, that is of lambda 1 and lambda 2. After resolution, the resultant will be R equal to 0 because they are no longer overlapping, since we have separated them using some optical instrument with considerable resolving power. Now, from this experiment, we can write that the magnitude of resultant maxima here is 0. Thus, resolving power is represented by lambda by d lambda, where lambda is nothing but the average of these wavelengths of these two overlapping colors, that is lambda 1 plus lambda 2 by 2, while the d lambda, this is the difference between these two wavelengths of these two overlapping colors, that is lambda 2 minus lambda 1. So here we can simply write that resolving power equals to lambda by d lambda. Now combining the two concepts, that is the resolving power of grating. As we know that in grating there are a huge number of parallel slits, that is like this, and after passing through these slits, that is after the light comes from the source and pass through these slits, it takes a, let's only consider single light ray for clarity. There will be other light rays from this source, but we'll only consider one ray for clarity. So after passing through these slits and slits, the light firstly normally reaches its uh, directed light path according to its properties to form the original image, say P naught. But after due to passing through a different number of slits at this point, it forms, let's say, two different diffracted images, because it's cutting different edges of these slits, and it takes different parts of diffraction with different angles of diffraction. Say it forms two diffracted images P1 and P2. Now here we can clearly see in this experiment that the first diffracted image, diffracted image, the diffraction angle is theta. For the second diffracted image, it is theta plus d theta. Also we can write the wavelength as for P1 it is lambda, then for P2 it will be lambda plus d lambda. Now since we've seen all the terms in this experiment of resolving power of grating, that is light coming from source passing through this different number of slits of grating, and after passing through that single light ray forms different images due to it's hitting different edges of the number of slits in this AB obstacle. It formed different diffraction images and an original image on the screen X, Y. Now, since we've seen the terms in this experiment, let's once again derive the formula. We know that path difference here is also the same, that is a plus d sine theta equals to n lambda, since a plus d is clearly is the distance between the two number of consecutive slits in this experiment according to the path of the light ray, which is equals to a plus d, like in the similar before experiments, that is a plus d sine theta equals to n lambda. And lambda here for the first light ray, and substituting these values in this equation, so we obtain these two equations. First one is for the difference between the magnitudes of these two images, that is these two diffraction angles and two wavelengths, that is d theta and d lambda. And second equation is directly for the P2 image, that is theta plus d theta and lambda plus d lambda. Now, the resolving power of the grating depends on ordering of weighting and total number of spectral lines. Thereas we can say that Rp, that is the resolving power of the grating, is proportional to small n, that is the order of grating is also proportional to capital N, which is the total number of spectral lines. So simply we can take these two equations as common. We can write that Rp equals to small n into capital N. Now, uh, the final concept in this chapter is resolving power of telescope. Let D be the diameter of the lens in the telescope. We know that a telescope contains lens. Let's D be the diameter of the lens, and theta be the angle of, and d theta be the angle of separation between the two objects. That is, let us assume through this telescope we are seeing two objects, and this d theta is the angular separation between these two objects. Now, the resolving power of the telescope is simply represented by 1 by delta theta equals to d by 1.22 theta, which is a simple default equation for this, for solving and getting different values of theta or delta theta or d for this particular equipment called telescope. Now, other equipment, there is other application of this chapter, that is resolving power of microscope. Once again, let's consider d be the distance between the objects and theta be the angle and n be the refractive index of the medium. So the resolving power of this microscope is represented by 1 by delta d equals to 2 n sine theta by theta. So that's all. These are the main concepts and main formulas with which we can solve many problems regarding these concepts in this chapter, diffraction. So in this way, diffraction also plays a key role in our daily lives with its many applications like telescopes, microscopes, and in many research fields. So diffraction, similar to the reflection or refraction and other light phenomena, also plays a key role in our daily lives. So thank you.